We're ready to start in a new chapter. In Chapter 3, we're going to be looking at the building blocks of matter. We're going to be looking at molecules, we're going to be looking at compounds, understanding the difference in that language, and we're going to look at chemical equations. We're going to start working with the mathematics of comparing how many we have with how much mass they have. So we've got a lot of work to do and a lot of foundational building information that we will use throughout the rest of your general chemistry experience. Now for section 3.2, this is a section that I need you to read and be responsible for. It's an introduction to chemical bonding, what holds these things together in those units of molecules or in compounds that are ionic. So you need to read about those, make sure you know the terminology associated with that. Take notes on that, bring those notes to class with you next time. But so let's get right on into the next section, 3.3, and talking about how we represent our compounds, how we use chemical formulas and molecular modeling to describe what we're talking about with these compounds. So what is a chemical formula? A chemical formula is going to give the elements in the compound. It's going to give you the relative number of each of those elements as subscripts. Most people are very familiar with chemical formulas. They've seen them in their background along the way. So here are some examples. So you're seeing the elements in it, H2O. Everybody knows that that's water, H2O. There's two hydrogens and an oxygen. We use the subscript after the element symbol to tell you how many hydrogens they have. And the next one is aluminum phosphate, AlPO4. And then we see C4H8. Each one of those are examples of chemical formula. Chemical formula is one way that we use to model a compound, okay? Different ways of representing these molecules. It doesn't have to be a formula. So let's look at an example of methane and see all the different ways that we can model that compound. The first is just the formula, which we just talked about. Now at the top it says it's a chemical formula. Because CH4 is a molecular compound, which we'll kind of describe the difference as we proceed. Because it's a molecular compound, it's not just a chemical formula, we call it a molecular formula. So that's what CH4 is. The next thing that we see over is a structural formula. The C in the middle with the hydrogen surrounding it is a structural formula. It gives us a little bit more information. It tells me that the hydrogens are connected to the C and not to each other. The third one is a ball and stick model. Now this is a real familiar one. We like to use this one a lot, but you need to understand this is a way of us kind of understanding what's happening in the three-dimensional state of things, but it's not a reality. It's not like there are sticks holding balls together. It's just a nice way of showing that three-dimensional arrangement of that central carbon and the four hydrogens around it. The space-filling model is a little bit more of an accurate way of showing that those atoms are really just bumping right up to each other and touching like this. So that is a more accurate depiction. Still, it's the model. It's not what the molecule really looks like. There's not a black center and white hydrogen surrounding it, but it helps us use that visual image to represent the molecule. The space-filling model has advantages, and that's a little bit more accurate depiction of the way the molecule exists on the, in the world of the molecule, but it's hard to see things behind because everything's so filled in. So sometimes we really like the ball and stick model a little bit better. Now when we use the ball and stick model, when we use the space-filled model that we see there, there is a kind of a guide of colors that is always used. The black that we see in the middle is always what we use for carbon. The white is what we use for hydrogen. Now you don't need to memorize these, but you'll get familiar as we go with those. If you run into oxygen, is probably one that we'll see more frequently. Oxygen is red, for example. Chlorine is green. So there is a kind of a standard color scheme for these kinds of molecular modeling. Okay, now there are two different ways that we can depict our formulas. We can use the chemical formula, which shows all the atoms and the subscripts tells you how many, and then there's an empirical formula. Now I want you to study these two formulas that I've written here for you. We've got the C2H6 and then the CH3, and I want you, as you study what you see there with what I've written for the empirical formula, think about what would be the definition of empirical formula provided that Okay, this is the empirical formula of this, both of them representing that compound right here. Now I've just got a couple choices. I want you to stop and I want you to think about it and pick what you think would be the right answer of what would define or describe an empirical formula. Okay, well, I hope that you chose B, the lowest whole number ratio of the atoms in the compound. A is actually the name of the chemical formula, the description of a chemical formula, the actual number of each atom in the compound using those subscripts to tell you how many you have. But it's kind of like reducing a fraction. You know, sometimes we might write something like, run across a number like 2/4. We would rarely leave it as 2/4. We usually reduce it down and say, well, that is the same thing as 1/2. Okay? An empirical formula is kind of like reducing the fraction. So as we look at, let me back up here, as we look at the empirical formula, we see that we've taken the 1, the 2, and the 6, and we reduce them down to, by dividing both by 2, dividing by the smallest whole number that we can divide into those, and that gives me kind of a reduced fraction, so to speak, just to use as an analogy. So that's what an empirical formula is. Okay, so with that as the description of an empirical formula, let's have you stop and look at these choices and tell me what would be the empirical formula of butane. Now, I've given you the molecular formula of butane, which is the same as its chemical formula. Tell me which one of those would be the empirical formula. Well, if you selected CH2D, you'd be correct, because if we divide both of these by 4, okay, we would have 1 carbon and 2 hydrogens. Now notice we don't write it as C1H4. If the subscript is a 1, okay, there's one of those things, we leave that subscript out. So it's just I shouldn't say 4. CH2. We don't write the 1 in there.